Hello everyone, thank you for coming here and being with us today. My name is Cyrus, I'm Principal Evangelist for AWS AI Labs, the Deep Engine team. The part of the Deep Engine I'm involved in is working on a product called MXNet. It's an Apache project. It's an open source deep learning framework. The other section of the Deep Engine is involved in Amazon SageMaker's development, and then I'm going to quickly go through what these things are and why they work well together. So we have our colleagues from Workday, Vivek and Henry, that the second part of the presentation, that would be their projects, and they would introduce the project to you. In this interest of time, so I'm going to, without further ado, trying to get into the talk and the agenda and what we're going to be doing. So in the first part, I'm talking about Apache MXNet, why we use it, why it's a good thing to use, and why people who use it think they should be doing that. I go through to the SageMaker as well as distributed training, because that brings out a lot of really good features of MXNet about the ability to be doing distributed training, and it fits very nicely with SageMaker. And then finally, it's about how it can fit into an end-to-end delivery of from research to production in one basically place. So let's start to see, back in the day when we were kids and I was studying neural networks, early 2000s and all, we could not really get large models or large data set trained for a very obvious reason, that we just had to do so much compute, too many basically processes, and we didn't realize that how we could distribute that. So every deep learning framework that you look at is on the basis of building something called a computational graph. So if you take a look at this thing that we have in here, if you're trying to compute T, then you need to compute U and K, and then to compute U, you need lambda and you need Z. But Z and K have no dependency on one another. If you can build a system, and when that system looks at what you're trying to compute, and discover all of these parallel paths that you can produce, and then you can parallelize the computation, then you can be a lot faster and compute so many things at the same time. And that is what made deep learning successful 2010 onwards for more industrial purposes. So if you look at this, is the symbolic code of MXNet. This is not Gluon library, this is Gluon API, this is the symbolic code of MXNet. When you look at that, it is basically you're trying to tell the framework, build me a computational graph, build me a fully connected, a dense layer, and let it have 64 nodes, and then you would have an activation, and then another layer, and then you would have an output for softmax that does classification for you. So you pass that to a deep learning engine, and it takes that and turns that into a computational graph with the parallel, basically figures out how it can parallelize it. And then next step, you're going to bind data to your model, and then when you bind data, it's basically the model is going to take your data and take the computational graph that it has created for you, and then is going to basically throw that on a GPUs that has millions of cores that can do these parallel operations of multiplication and addition of floating point numbers to one another. And that's how generally is the foundation of every deep learning engine that you're going to use, whether it's going to be TensorFlow or MXNet or something else. So why do we use MXNet? We use MXNet firstly for training efficiency. So this graph represents the efficiency of making use of distributed hardware. So an ideal distributed system is when you have a linear relationship between the amount of hardware that you throw at it, the amount of compute that you throw at your problem, and how faster you get. So that means if you double your hardware and you can make your training, halve your training time, that's ideal because that's a linear relationship. Then if you look at it on 256 that includes things like network latency, and all of that. What we have ended up with is a 92% efficiency for ResNet 152, which is a very large network. That means as you basically through twice as much compute, you become 182% faster. So that means it's almost linear for such a huge model. So that is training efficiency. And training efficiency, if you do your modeling correctly, is going to hugely reduce your numbers. I can give you an example we had in Japan that were just a few tweaks for a company in Japan that we made their training more efficient. They had a projection of 22 million a year saving on the compute money that they were paying, that sort of stuff. So that can be quite expensive because these beefy GPU machines are just pricey, and the more you can utilize them, the less you pay for your training. Then, adding to that, there is Amazon SageMaker. So Amazon SageMaker is created as a zero setup tool that can have an end-to-end environment for you, and it can do a lot of distribution for you. It builds a distributed cluster, and it trains your model in a distributed cluster, and it adds security features, and it would be in your VPC. So all of that cluster that you want to build with the security on the top, you don't have to do any sort of configuration for it, and you pay by the second. So you're done, your cluster has been created, the training is done, the training is finished, the model is saved into an S3 bucket, the cluster is destroyed, and you pay for any second, basically for the number of seconds that your cluster was up and running. So, and then we talk about the training efficiency. One of the, probably the biggest bottleneck you have for training a distributed system is your I/O, because your compute is fast, but your I/O is not going to be as fast. I/O is going to be your bottleneck. Most of the optimization you do is there. So we introduced in SageMaker, when it came out, some built-in algorithms. And then last summer, during the New York Summit, we introduced something called streaming. So streaming is when S3 to your training instances is basically quite fast, and it can send your information to different basically nodes that you have. And then as of last summer, we introduced streaming for custom algorithms. So what you see in here is for one of the built-in algorithms for the PCA algorithm. You can find that in a blog post, and there's a reference to that. As you see here, the whole bunch of indicators are getting better, whether it is the time to start of your model, whether it's basically the amount of data that is streamed. So we introduced that to your own algorithms too. So that means you can go and develop an algorithm and then use the streaming for custom algorithm in order to use the efficiencies that is built into connection of S3 to Amazon SageMaker in order to not to starve your GPU instances. The way distributed training goes about is that you have your models in S3. From S3, you have your code basically somewhere, and then your data is going to be streamed or copied into your basically nodes of your training cluster, and then your model is trained, and the result of that model is being put basically in an S3 bucket. And the way it's done, it uses an ECS cluster, an ECS cluster, an Elastic Container Service. And then this cluster can be within your own VPC. The connections can be encrypted. And all of that extra securities that you would be normally building in your cluster, and all of this basically efficiency of the data and connectivity and the location that you want to see when your source of your data is, how far your data goes to reach the server, all of that is done behind the scene for you with a single line of code or a single click. So you don't have to do anything about it. You don't have to worry about it. You can focus on developing your model. We also introduced something between last year and now, automatic model training. So I do have a basically talk about that get very scientific about it later on. But what we do in here is you have, let's say you have a stereo that has 32 different volume knobs, and you want to make the best sound out of that. And the permutations start going mad. And the same thing goes with the hyperparameters of your model, that you want to basically do hyperparameter optimization. And every time you introduce a new hyperparameter, what you end up with is exponentially increasing the number of permutations you're going to have. And you get into this curse of dimensionality and basically based on the laws of multiplication. So what we do in here, we have used a Bayesian hyperparameter optimization that builds a machine learning model that looks at your model as they're being trained, and it figures out and locks in which of these parameters will work best for the results of your model. So it uses machine learning on the top of your model and uses machine learning to figure out the best combination of hyperparameters. And that used to be hundreds and hundreds of hours of scientific work for just little tweaking and waiting for another training to go through to see what the result is. Oh, that wasn't good, let's do it the other way. So, and since this is a Bayesian model, it's just very efficient with the number of samples that it takes. And it very quickly zeroes in with a very few, basically, iterations to figure out where those hyperparameters are at their best in terms of efficiency of your model. So this was all about training efficiency and how you can train better. How about the developer productivity? Should your developers spend 80%, 85% of their time sitting down and just thinking about what went wrong with my model and I have no way of debugging it? Or should they spend 80, 90% of their time doing something new and doing less debugging? And here is the evolution of frameworks. So early on, there was the good old Theano, and then came Caffe, and then came CNTK. TensorFlow made a case for an industrial grade deep learning framework with one thing. It was something called symbolic, that you just did like the code that I had created before. You create a network, you bind data to it, and then you have no idea what's going on. And then at some point, it tells you in the layer 3 to 5, I have a shape error. Good luck figuring out what's wrong. So these are the symbolic ones. So MXNet's core is the same way. Keras is a high-level API, but it still does the same. Then came the next move that came by Chainer. So Chainer introduced something called imperative model. So how it works is that it's like the way we're used to coding. If, then else, and a for loop, and an iterator, and that sort of stuff. So breakpoints, you can debug it. But they lost the performance of these models that were building this computational graph behind the scene and optimizing it for distribution. PyTorch is the same way. Then came Gluon. We developed Gluon in 2017. We released it as a part of the Apache project to which I belong. And Gluon is a high-level API, very similar to PyTorch, but it has this thing that you can take your network and just say network hybridize. It suddenly changes from the imperative mood to the symbolic mood. So it combines the best of the two worlds. It's like very friendly in terms of developers being able to develop things quickly and well, while at the same time it gives you all the performance that you want to get from a symbolic framework. So bringing the best of the two worlds together, so your model from your experiment to your production remains within the same boundary, so you don't have to go in and out and just convert things together. So why we use Gluon? I already mentioned a few of things. So the code is easy to understand, it's flexible, it's got imperative structure, it's got dynamic graphs, which is quite nice because you don't have to statically calculate what is going to be output of this layer, what is the input of the next layer. It dynamically calculates how the graph should look like. And it has the same high performance of MXNet in its symbolic mood at the end of the day. That's why Gluon, we think, is a very good place to start your coding. The code that we saw before, or this is how the basically code looks like. So that would be very familiar with the PyTorch guys in here. So I am building here a basically network. It's a hybrid sequential network. That means I'm stacking layers sequentially, but I can hybridize it in order to make it symbolic. And then I'm adding a dense layer, a fully connected layer, 64 nodes. Activation is ReLU. And then I have a discrimination layer that I have basically 10 units at the end. That's my output. That's where I want to do a classification for 10 classes. And then I can, all different sorts of loss function I can assign in here. I can have initialization of my model with basically different sorts of initializers. In this case, Xavier. It could be all random normal. It could be random uniform. It could be just simply zeros. It could be a fixed number. Or it could be the tensors that you have gone from the weights of another network you have trained, and you can start with the basically weights of a different network, which is used in the likes of transfer learning. Then you can have a choice of that trainer, that would be your optimizer, so you can have stochastic gradient descent, you can have Adam, you can have RMS prom, as well as there are some optimizer that are built for cluster and large-scale training. For instance, there is Zignum that is using only the sign-off gradient and is used for large clusters of training. If you're doing it, is a lot more efficient because it's just bits that going around rather than the whole floating point numbers for your gradients. So it's a lot less noisy in your network. Or there is the big SGD that is made for very large batches of in the range of thousands. There are also things like the learning rate scheduler that you can just pass your learning rate scheduler to your optimizer object, and then it just does all the scheduling automatically for you. You just have to decide how you want to schedule your learning rate. So that is really, really quite easy. And then here is the for loop. Here's where the magic happens. This is where you're doing a training, and the training you have in here is a for loop. That means you can actually put a breakpoint in there and just look inside your variables to see what's going on with your code, what's wrong with your code, why is the error that you're getting, and makes the developers a lot easier to work with. The developer productivity doesn't stop here because we are continuously creating toolkits. Like we recently introduced the Gluon CV. It's a deep learning toolkit for computer vision. So we have implemented and optimized a whole bunch of famous networks like the VGGs and ResNets, and we have optimized them so you can use them for transfer learning for a model, or you can just use them out of the box. So hours and hours of basically optimization and training compute time has gone to these models, so you can just use a model zoo and say, I want to use a VGG 16 and just use that. The other things that they have, apart from pre-trained models, they've got lots of utilities that are useful for computer vision, like for instance, data augmentation utilities and all of that. It also has a whole bunch of the public data sets that are available to you through the data library, so it's the data API. So if you want to do an experiment very quickly on a public data set, you can use Gluon CV in order to do computer vision. Gluon NLP, very similar for NLP tasks. For basically, it's got basically the embedding capabilities, it's got the pre-trained models, and it's got the data APIs, and the same sort of thing for basically rapid development of prototypes. So that doesn't stop here. We introduced recently Keras Backend for MXNet. And what you see in here, there is some from GitHub. You can see some of the comparisons that we have done for different sorts of batch size that we have in here. You can compare TensorFlow backend to Keras backend, and you see as the number of nodes go up, like when you go to this basically batch size of 256 and 8 P316X large, compared to the line before that, you see still showing image per second processing. It's just still going up in MXNet while it started reversing in TensorFlow. You see that basically the processing is so much faster. So all you need to do, if you change your backend, you get the benefit of the performance. So in some project I was doing in Portugal, we just changed the backend for that specific model, for that specific data set. We just doubled the speed. So that sort of stuff. It's not guaranteed always, so don't get me that I'm saying it doubles. It's just an experiment from one project we were doing. So what else? There are things apart from the Gluon NLP that provides you a natural language processing component. We have also produced something called a sequence-to-sequence toolkit based on Apache MXNet. My colleagues in Berlin developed that. We call it Sockeye. It's in GitHub. And this is the thing that is behind the translation we do in Amazon Retail. So we have made that available to you. You can actually go on in GitHub and just use it. You don't owe anyone anything. So, and these are the stuff that we have done around MXNet to make it available for everyone and make them very basically developer friendly. It doesn't stop there. When we talked to the customer, when we started developing these things, we were thinking very academically. So we were very much focused on the training performance. And the more we worked with the customers, it came that, you know what, I really don't care much about training because I don't do a cluster of 256, but I really care about inference. I really care about that, how easily I can deploy that. Then we started working very, very heavily on the performance and the diversity of the inference that we do. So here are some of the most recent developments that we've done. So we released TensorRT. That TensorRT makes basically makes better use of your inference GPU for inference. As you see here from ResNet 101, that it doubles the speed for inference if you use it basically if you use TensorRT compared to not using TensorRT to the slowest, that is AlexNet, that is 1.4 times faster for your inference. And inference is your bread and butter because it might be your customers are exposed to the inference endpoint. They can't wait. They go somewhere else. So that is TensorRT. That's one of the more recent implementations. We move forward. So there is NNVM. You will hear more about it. One of the things that we do in here is we compile the models for the target hardware. So with a line of code or two, you can say, I want this thing to go on Atom or Raspberry Pi, or I want it to go beyond Pascal, or I want it on this and that. It does create an optimized model for that. Basically, your model would be optimized. The output, basically your model artifact, would be optimized for that architecture, the target architecture. So that means you can have efficiency on multiple outputs without having to tweak it. Yet again, I'm not claiming you cannot tweak it and get better manual results per architecture, but try to imagine the efficiency of just saying, oh, I want this model to be on Raspberry Pi and on basically Voltas and on a Pascal and on this and that. So it can actually does the compiling, recompiles your model for the target hardware that you're going to run on it. So that's another things we've done. Then there is portability. It doesn't end here. You want your models, you don't want to be locked into a model artifact or locked into a certain hardware. So we should think about portability. So again, through NNVM, we have developed that. So when you look at these two, so you have a computational graph, and when you have an abstraction layer through NNVM, through basically the compiler, you can actually move across different sorts of hardware. I just mentioned it. Not only is it efficient, but it also makes it possible. Otherwise, you have to be tweaking everything by hand until you get something right. You have to know every hardware you're working with. And let's say what you're doing, you're building an app that is trying to do some computer vision. Do you really want to spend your time trying to learn about every hardware that is out there, or you want us to do that for you and you just compile the model for the new hardware? Portability comes also that your model artifacts can move between different models. If you're PyTorch shop, sure, just continue developing in PyTorch. You don't have to move to Gluon. But through Onyx, you can actually get your you can get your model artifact from PyTorch and just make the inference with MXNet, the deployment, and use the benefit of the speed of MXNet while you continue coding in the environment that you actually like to work on. So finally, we're going to the deployment. So deployment with SageMaker is that you can have a complete DevOps environment. You can say, I have created this model. I want to deploy it. It's one line of code and some configuration if you want to add something to it. And what it does, it creates a cluster, the Dockerized cluster, Dockerizes your model, drops it into these nodes, puts a load balancer in front of it. It creates basically a microservice architecture entirely with a single line of code that you just say deployment model. And it doesn't have to be developed in SageMaker. It could be your own model that you go and just package it as a Docker image and you bring it in here. And then it just does that for you. So you can have A/B testing. You can blue-green deployment. You can say, I want to have multiples of profile. You can have the percentage. 20% goes to this model. 50% goes to that model. 10% to these models, that kind of architecture. So all of that thing is done really without you having to worry about it. And it's auto-scaling, so that means more traffic coming in, you would have more nodes. Less traffic coming in, you go back to the minimum that you have decided. There's one more thing I haven't had in this slide, since I have still 40 minutes to go. We have made MXNet polyglot, multilingual. We realize that there are statisticians who work with R and they don't want to use Python. There are people who want to use Perl. There are people who want to use Java, Scala. So the actual high-level API comes in all different languages. So you're no longer bound to it's Python and it's Python and it's Python. So we have created all of these language APIs that you can actually use, and language of your choice for developing your Gluon MXNet models. So to recap, so MXNet gives you the engine. the fast engine underneath. Gluon gives you the developer productivity, and Amazon SageMaker brings that together in an enterprise-grade environment with an end-to-end DevOps, as well as adding hyperparameter tuning to you, and the hyperparameter tuning, again, is just another line of code to add to what you do. So the whole thing comes together quite easily for you to be able to focus on developing efficient models as opposed to thinking about computing gradients, or I don't know, just building a Dockerized cluster, an ECS cluster. So by this, my part is done. I'm passing over to our friends from Workday, and they would explain their project to you.
Thanks for coming. I'm Vivek Srivastav. I'm a machine learning product manager at Workday, and my partner in crime is Henry Zhang. He's a machine learning engineer at Workday. Essentially, the whole purpose of building a machine learning solution using MXNet is to simplify and automate some of the processes that we have in Workday. One of the key things that we identified early on was information extraction for enterprise documents. So that sounds kind of very abstract. So before I get into the details, I just want to show of hands of how many of you actually know what is Workday. OK, that's great. So a lot of you know it. For those who don't, Workday is a company that provides HR and finance applications for your enterprise. And it's a cloud provider of your HR and finance business applications. It runs your HR and finance business applications in the cloud. So the basic goal when you talk about enterprise documents for an enterprise application, it's quite varied. Think of, say your company has Workday or subscribe to Workday. One of the things we provide you as a user is to submit your expenses. So you would log into Workday, submit your reInvent travel expenses. So the document there, or Workday, becomes a source of truth for storing and processing your receipts. So typically what you would do is you would manually enter all that information in that receipt. Take an example of an account payable department in your company. They tend to process a lot of supplier and vendor invoices. When your company buys certain products, they get an invoice. That invoice goes through a processing piece. And Workday is the platform where you store and process that document. And in the end, you make that payment to your supplier. The third offering, if you think about it, can be, so Workday has an end-to-end recruiting solution where a recruiter basically will use Workday as a single source of truth to store and process resumes of potential candidates who have applied to your job recs that the recruiters put out. So you have all these enterprise documents that get generated within Workday. We store them. Workday users tend to process them. But we found out that by using machine learning, specifically deep learning, we can actually improve the efficiency of some business processes that lead with or that deal with these documents. So I'll talk today about two of the specific use cases that we have built a machine learning solution for, especially using Apache MXNet. So the talk today, I'm going to speak a little bit about the business case, a little bit more deeper details on the first one, which is going to be your expense report automation. So how we have automated that process in Workday. And the second is going to be the invoice processing automation. So how, by using machine learning, we are enabling that to get automated. After that, Henry will come forward and talk about the framework we've used. I guess no guesses. We're all here because we've used Apache MXNet. The third we'll talk about is the model and how we build that model and the algorithm for that. And we'll talk about the results we've achieved in terms of accuracy, for scanning the document and identifying appropriate fields. I'll come back to talk about how we have productized this entire thing on the Workday stack. So essentially what Cyrus was talking about in terms of running inference on the Workday stack and high-performant inference, and some key learnings from that. So let's take the first business use case. So typically, an expense report filing process is a user logs in, submits a receipt, manually enters fields like amount that was spent, where the expense happened, and the date the expenditure took place, and submits that report. That goes through an approval from a manager, goes to the finance department, accountants take a look at it, and make sure everything is kosher, and then the reimbursement check comes to your bank or to your house. So what we identified when talking to customers is that some of the top travel and expense pain points was employees either lose the receipts are crumbled and kept somewhere, there are errors manually entering that information. So all of this, in short, basically, it takes time to reconcile simple things like filing an expense report. And time is money, especially in the enterprise world. The second business case is the accounts payable invoice automation. So in Workday, we deal with invoices basically in the thousands per week for some of our large customers. The process of invoice processing is the typical business process is quite involved and involves multiple touch points. The invoice is scanned. The various fields in the invoice, including each line item, vendor name, is all manually typed. And then that invoice is then routed to the appropriate accounting department of the cost center. And it then goes through a review process, a code is attached, and the invoice is finally approved. Once the invoice is approved, it gets entered as a journal line in your general ledger. So all of this happens within the Workday system, but the business process itself has a lot of manual steps. So what you will see is basically how we have used machine learning to at least automate parts of this process so that this process becomes less painful for our customers, and it leads to more efficiency overall when customers are using the Workday product. So the solution we have basically used is twofold. They're all based on computer vision and NLU. Computer vision basically for when a document is presented, you have no idea what the document is. It could be a receipt, it could be an invoice. So computer vision to basically extract boxes of text from the document, and NLU to understand what the text means so that when you upload a receipt, we can auto-populate the amount, the date, the merchant name, for example, and all you have to do is click submit. Same thing with invoices. We can auto-populate the vendor name, the item number, the description for the item, and the price. So I'll now invite Henry to go into how we built this solution.
Hi. Yeah, so the first step for a machine learning application, especially that has deep learning involved, is choosing framework. We are already over the era of Theano and Torch, which are very good for research purposes, but incredibly difficult to productize. So for us, our requirement is, number one, it has to be fast and agile in prototyping and experiments. In my opinion, if you're solving a state-of-the-art hard problem that already have solution, that's not very hard because you can just take the solution that people already have. Or if you're solving easy problems that can be solved, say, by logistic regression or decision tree, those are not very difficult either because a lot of people have experience with them. But the difficult problems are if you want to solve problems that are slightly easier than a lot of the hardest problems, but no researchers actually care about doing them and making improvements on the state of the art. So, for this applied research purpose, it has to be fast and agile. And as we are a Scala shop on the JVM language, we would prefer to have the framework to be able to just productize immediately to JVM language. And also, of course, for the same type of model, we want the best accuracy and the best optimization that we can get. And as you can see, I'm not mentioning performance here, that it's not that performance is not important, but rather we place accuracy as the top most important metric, given that for enterprise, things have to work. And ideally, and because there's not that many very mature frameworks when we made this decision, which is around maybe end of last year, we would appreciate some support, but really we understand it's very difficult. So we ended up choosing MXNet because it can use Python to prototype, and we can immediately export the model and have it loaded on the Scala API and just use it immediately. So MXNet is agile because it's imperative. So if you look at TensorFlow back in the days, it's a graph computation library. But if you want to take parameters, say, in the middle of a stage, it is very, very difficult. So MXNet is imperative, and now so is PyTorch. So both of these frameworks kind of solve this problem. And as we compare the training speed and inference speed for our problem, we got a 50% faster using MXNet versus TensorFlow, as well as memory consumption. And also, as I will show later, it has better accuracy for our problems. As we progress into the project even further, we had to use encoder-decoder models, which we found the Sakai framework from AWS AI Labs to be very helpful. And one thing we didn't expect out of this framework choice is that we actually had strong and active support from the AWS MXNet team. Yeah, so this is a table showing, and by the way, I put the year there because frameworks all progress, so I just don't want this to be taken out of context. But at the time we made this decision, we actually thoroughly compared the two frameworks. And these numbers are, because they're error rates, so the lower the better. I just want to make it clear as well. So MXNet performed a lot better than TensorFlow. So this is why we end up picking it. And our problem is more about recognizing the text. So generally, we look at perfect match and editing distance. Yeah, so next I wanted to talk about models and algorithms. So essentially, we're solving three problems, right? One is, where are the texts? This problem is typically solved by template matching in the past for enterprise software. So you take each type of document and you create different templates for the different variety, and then you run a statistical model on it to figure out which template is the most appropriate. And the next part is, what are the texts? So this is a well-traversed problem for deep learning and neural networks, even back in the 80s. However, recently there's some improvements in this as well. And the third part is a natural language processing problem. So once you recognize the text, what do they mean? What's important? What you're really looking for? And this differs between application and applications. So the first problem, where are the texts? So our model is a customized, you only look once network. And what we customize on that is instead of using convolutional neural network, we put a residual net instead. And we also added an additional output, which is the angle of tilt. So this is very important because when the user takes a photo or they scan something, it is possible for that image to be tilted. So in the consumer space, if you're looking at, say, tagging a face in a photo and saying, hey, this is Henry or this is Vivek, you don't have that problem because as long as you have the box on the face, you're fine. But for enterprise, we can't just box it and have it tilted. It's going to affect our end-to-end accuracy by a huge margin. So we added angle of tilt, and as well, we have to make the same modification in our training data to make sure that our model is able to capture and find out how tilted the model is. The second part is, where are the texts? We have a customized model based on WaveNet, which is originally intended for speech. However, we're able to modify that and adapt it to a sequence of pixels, which end up being the words that's being read. Now, the last part is, what do the texts mean? And there are multiple approaches we're applying for this, and the first one is rules-based systems. So for, as much as there's a lot of hype on AI and all these magical stuff, but I'm looking at, both myself and everybody here, we still do a significant portion of our AI in rules-based systems. So essentially, we're looking at surrounding context. So give an example, if you're looking for a certain date, the dates have a certain format to that, and there's certain surrounding context. So we combine rules-based along with fuzzy regular expression. The reason for fuzzy regular expression is because it is possible for you to get error from the text reading process. Now, the second approach we use is a encoder and decoder, sequence-to-sequence approach. So with attention mechanism. And we actually trained the model with the character embedding to word embedding. So, and also the vocabulary is built with the training data itself. Now, the future work of this is to expand it so that we can apply the embeddings of either fast text or word-to-vec. However, I think now you can also do bidirectional transformer, which is kind of like a different, a newer thing now. Yeah, and the benefit of the encoder and decoder approach is that it's very good at inferring from context. So if you look at the receipt on the right, we as humans know that this is an Uber receipt because we know the color of the app, and we know that in general the screen is structured. However, if you're doing this with a traditional machine learning approach, there is no sign of Uber here, right? So this approach is really good because it is able to recognize from the training data, hey, for Uber, this is what the context in general look like, the order of the words and what is being talked about. But there's a drawback of this approach as well, which is if you do not have Uber in your training set, then it cannot do anything, right? So let's say in the next year, Waymo has their self-driving capability perfected, and somehow we're slacking and we don't have Waymo in our training set yet, then probably we're able to figure out it is some ride-sharing app, right, like Uber or Lyft through the context, but we're not able to figure out it is Waymo because we never had that label. So we have to employ a different approach to handle that situation. And that situation, and how we handle that is we use a CNN-based approach to classify each box that we recognize. So when we first figure out where the texts are, we take those boxes and we do some classification on that. And we leverage the word-to-vec embedding. So this approach will consider both language context and also approximate location of each field. So in the case where it does not find a label that currently exists in our training set, it's going to make a guess on, in the past, roughly where the field that we have interested in is at for that particular type of receipt and for that particular context. And now we clearly have three approaches, so this is how we use them together. For easier fields, rule-based is very sufficient, so we just use that. And for more difficult fields, the encoder and decoder approach, we can get some sort of confidence of how well we think this result is correct. And if that value is not confident, then we will take, finally, the CNN box tagging approach. So with only 40K training data, we're able to get 72% accuracy on the test set. And the number seems very low, but our test set is actually a very difficult test set because we got a lot of receipts that are essentially very noisy because we want to make sure that when we release this to the customers, we actually test it on a set that is harder than what we would expect. And because we don't have a lot of training data, we had to employ transfer learning. So we wrote a script and took a bunch of photos that our team took randomly in the past. We contributed our own photos for the fun of it. And we essentially put words on it. And we generated a few million of these. And we trained the model on these images first to recognize texts. And then we fine-tuned on the 40K, 50K of real data that we have. So these are the examples of real data that we're dealing with. Now, results. So we have very competitive results that's at least on par or on average even performs better than a lot of major public cloud providers on the vision part of the model. So this proves that for our specific problem, if we just use a public cloud provider, we actually would have gotten a less accurate result. And also for the test set metrics, depending on the reason why it varies is it depends on what field you're looking for, because we're looking at end-to-end metrics, not just specifically the vision part, but also NLP. So depending on field, we're looking at 75 to 85%. And for production, so we got this number from how many times it gets changed on the app side. So we have metrics for that. I mean, everybody is data-driven nowadays. So as a result, only 5% of all the receipts are ever changed. So this is how we measure, in the end, what is our production accuracy. So I guess one of the key takeaway here is always make your test set more difficult than what you would expect. Okay, so now I will hand back to Vivek for productization.
Thanks. So we have 3 more minutes. Want to leave 10 minutes for questions. So quickly, I'll talk about how we productize all of this, the model building, training part, and the Workday stack. So this is a live stack. This is how actually it's running today in the Workday product. So this is more system level. So basically, we leverage MXNet service, which you see at the far bottom for inferencing or prediction. We leverage it in multiple ways. So we use Kafka for the image coming in. We fetch the image from a data store. And the first 3 boxes that you see is essentially an ensemble of the same model where we scale the image 3 times. And FOI is field of interest, so essentially what fields we're interested in. It basically detects all the text, the blue stuff you saw in Henry's slide earlier. We then call the next stage, which is you actually extract that text in the text inference stage. And all those models are, again, served by an MXNet server. So we set up that MXNet server, which just takes in the model, takes in input parameters, which can be image or the coordinates of the image, does the compute magic, and returns back. In the first stage, it returns back the coordinates where those small boxes are. In the second stage, it returns a JSON of all the text. And the third one, essentially, is the parser, which is the Ensemble strategy that Henry was talking about, that again uses the MXNet service that feeds in all the text. And specifically, and here's where the business part comes in, we are only interested in, say, for example, the amount or the merchant name or the date. We don't care about other text. So the parser is what basically extracts all that and puts it back in Kafka. And then we return that back to the application, the Workday finance application that is consuming those results and showing it back to the end user. What were the key learnings from this? First, we found out there's a lot of value in building models specifically for our own business or product use case. So customized models went far more, especially in the enterprise case. We were able to achieve production accuracies of 95%, which is pretty amazing, and our customers are pretty happy with that. The second one is there is a lot of difference between running a model, training a model, writing some experimentation code, not knowing which one to pick, doing that quote-unquote research. But when you actually want to put it in production, it's a whole different ball game because now you're talking about customer-facing application. You can't willy-nilly go change things so fast. So that was one big challenge that in machine learning application, everybody focuses a lot on the model and the AI part, or the ML part, which is great. But the supporting systems also have to be built to actually make it work and scale. And that's something we learned by developing this particular feature. And the third one was, I think Henry alluded to this, we pretty much had like daily scrums before go live with the AWS MXNet team in February. So this went live March of this year. And they were really helping us because we were one of the first adopters of their Scala API. So our backend is entirely in Scala. Just hashing out issues that we have faced or we uncovered while we were productizing the MXNet service. And they were available, and that was great. That's it. That's the end of our talk, and I open it to questions. Yep. Can you use the mic if you don't mind?
Hey, thanks for the talk. Quick couple of questions. What do you do with handwritten totals on receipts, especially adding tips? It's not always kind of obvious to extract. Secondly, is there a mechanism for you to do A/B testing on the machine learning models? Because you have customer-facing service, right? Is there a possibility of doing that with the frameworks you have selected?
Sure. You want to take the first one?
Yeah, so in terms of handwriting models, so essentially we're looking at the second problem, which is what the texts are, right? And that is already a quite well-traversed problem. So currently at our MVP stage, we do not support it, but the model is actually, again, this is a problem where I would place it as it's very well-traversed. We don't have to do a lot of customization. So it's a matter of essentially another release.
And to take a second question, if you look at the productization part here, so if you look at the MXNet ML engine, and you see the model store, that's basically where we allow A/B testing on models. So you can put your models, so this framework or the system we built, your model store can have different versions of the model for the same application, and just through REST API calls, you can actually retrieve that specific model, send the same data, and test it and compare, and then you do a switcheroo of which one you want to serve in production. So.
Thank you.
Yep. Yep.
Hi, I have a question regarding the accuracy. So the machine learning models are not 100%. What do you do with that, say you have 85%, what do you do with the 15%? And in the production environment, how do you identify that a image is part of the 85 or part of the 15%?
I can take it if you want.
Either of us.
Yeah. So essentially, that's a very good question. At least on the production side of things, right? We have mechanisms in place where when a user corrects the value that we have returned, we capture that action, and that for us becomes a feedback loop, right? Where we take that input and then retrain the model and improve the model itself, right? So part of that feedback loop is also getting the image and checking basically if we have trained the models on that. So that's kind of how we do it today, where we get that data of what the user has entered.
Yeah.
So basically there's a verification process somewhere?
Sorry?
There's a verification, like a manual process to verify the...
No, it's all automated in the Workday product itself. When there's a value which is, are you talking about comparing to what the actual ground truth was? Is that what you're saying? Or?
Right, so when your model is not 100%, you always have this fear of something is wrong, right?
Yeah, so Yeah, so can I add
Yeah,
to
sure.
that? Yeah. So I think what Vivek mentioned is that we can certainly get a feedback loop and train the model further, and I think the accuracy will increase over time. But I think your question is that it will never reach 100%, and what do we do when it fails, right? So I think this has something to do with our vision of how machine learning fits into enterprise software.
Yeah.
So it's never meant to replace people completely, but it's meant to assist you. So I would actually say this is more of a product design, right? So when you design a product, do you make machine learning your default, or do you make machine learning something where it's going to help, but then in the end, the user has to verify and make sure, hey, this is not giving me results that's essentially nonsense, right? So and actually, I want to add on top of that, and there's it's a heavily researched topic right now, is that. And we have been doing testing on our side as well, is if you send in a photo of a cat instead of a receipt or an invoice, right? Or if you send in, can you break it, right? And this is actually a very heavily researched topic, and because of that, you never know if it is possible that you send in something that it's going to, get the deep learning model to do something that's unexpected. So that being said, we do not, at least for enterprise, and this is our vision, we don't want machine learning to be a replacement of what humans do, but rather to help and assist.
Thank you.
Actually, I was going to ask the same question if you were using adversarial networks to test your model, and also whether you have incorporated in your results a confidence interval of the prediction, and whether you use exception handling as part of your workflow to bring humans into the loop where there are low confidence in your recognition.
So today in the product, we don't have any humans in the loop to rectify things, right? We directly expose. Let's talk about the receipts use case. Mm-hmm. We directly expose it to the end user, and the end user can go change the value, right? With the kind of accuracy we've been hitting, we haven't had a lot of support tickets come our way, so I'm happy about it. But yeah, there's absolutely zero human in the loop in production. Does that answer your question?
And then the second question, I guess, using adversarial networks to generate data to reinforce your model to avoid false positives.
Well, that story is actually on our backlog. The reason I have hesitance of using that is because as for enterprise, things have to work, right? So I personally have, I would say this is something we definitely should research, but at this moment, and I think there was just recently a breakthrough maybe 2 months ago about image generation from using GANN. But I think in the near, say, a year or so, it might become a reality. But right now, for us to generate those images, I have some doubts on on the quality of the training data from that.
May I just butt it into that? So usually what you're lacking in the data generated by GAN is lack of entropy. So the real data you get from the world, it's got entropy. The stuff that GAN produces is very much focused on whatever it is that it's supposed to do. There is very little extra information in there. I've been scanning for research around, and there are research about how to introduce entropy in your GAN-generated data. A couple of years maybe, we don't know how long, but there is that people are seriously thinking about it. Yeah. And if you want to research that area, look for introduction of entropy to GAN data, and then you might come across a paper that has similarities to what you want to do. But that's your major problem, that that you might not be able to create data that is very similar to what you have. There's research. There's research there. Yeah.
Last question.
Yeah, we have 50 seconds. Go ahead.
Keras has a Keras Fit where you can do incremental updates as well, allegedly, to their model. Does MXNet have the same thing, and are you exploring using that?
Sorry, what is the incremental update?
Where you could take your model and add additional training to it without starting from scratch.
Can you explain how it works? I'm not very familiar. Sure. I'm not very deeply familiar with Keras, but what is the task that you do?
The idea is to improve your accuracy by adding additional samples into it, but I'm not so sure it's smoke and mirrors. I've not used it directly myself. I'm just wondering if MXNet had the same.
email me, I'll figure out the answer for you. I don't want to answer something I'm not very well aware of. So thank you.
OK. Thanks for coming, guys.